Hi, this video lecture will give you a good introduction to concepts of principal stress, principal plane and Mohr circle analysis. So let's start. First, concepts of principal stress and principal plane. Consider this problem, a structure under given loading condition, and assume the engineer who is in charge of design of the structure wants to predict whether this structure will withstand this given load at this point, at the right point. And if he wants to predict that, first thing he has to calculate is maximum shear stress and maximum normal stress induced at this point. So that's the aim. We want to determine maximum normal stress and maximum shear stress induced at a given point. First we will see how to determine maximum normal stress induced at a given point. Along with that we will come to know how to determine maximum shear stress induced at the same point. And you know stress is always defined on a plane. So first we will have a look at planes passing through this point. Here it is. This can be one plane passing through this point. And this can be another plane, this can be another plane. In fact, there could be infinite number of planes passing through this point, and normal stress values on each plane will be different from one another. But there will be one plane on which the normal stress value will be maximum, and that plane will be known as principal plane, and normal stress on that plane will be known as principal stress. Similarly, there will be one more plane passing through the same point on which normal stress value will be minimum. This is also a principal plane, more precisely minimum principal plane, and normal stress on that plane will be known as minimum principal stress. In short, you can define principal plane as a plane at which normal stress value is maximum or minimum. And this is a three-dimensional problem. Stress analysis of a 3D problem is pretty complicated. So what we will do, we will take a 2D problem, we will do stress analysis of a 2D problem. We will learn how to predict principal plane and principal stress for a 2D case. We will learn it well, and we will come back to the same problem, to the 3D problem. So let's get into it, the 2D problem. So the two-dimensional stress analysis. This is a two-dimensional object where I have to do stress analysis, and stresses acting on boundary of this object are a normal stress along x direction, sigma x, and another normal stress along y direction, sigma y. Finally, shear stresses on four planes of the body, tau xy. Now in a stress analysis, what you have to determine is stress at any plane inside the body. Plane can be this or this, anything like this. You have defined a plane which is angle theta with vertical, the dotted line, and you want to know what's the shear stress and what's the normal stress at this plane. Well, you could evaluate these two quantities using simple force balance, but that method will be too tedious for engineering problems. Most effective and easy method for this purpose is one graphical method known as Mohr circle analysis. Let's see how we can use Mohr circle analysis to solve this problem. First step in Mohr circles method, draw two axes. One is for normal stress, that is horizontal, and another for shear stress, that is vertical. A positive direction of axes are shown here, and negative will be in opposite way. Second step, mark normal stress values of your problem over the horizontal axis. Means you have got two normal stress values for this particular problem. So mark values of that over here. And please note the sign convention. If stress is tensile in nature, then we should mark in positive axis. And if it is compressive in nature, we should mark it in negative axis. And for this problem, both the stresses are tensile. That's why we mark it on positive axis. Now the third step, draw shear stress values parallel to the vertical axis. Start from the already marked normal stress values. And about sign convention of shear stress values, if shear stress tends to rotate that body in clockwise direction, then it will be drawn as positive value, and if it is trying to rotate the body in anti-clockwise direction, it will be marked as negative value. And in our problem on y plane, shear stress was trying to rotate the body in clockwise direction, that's why I marked it in positive way, and opposite is true for other case. Now the fourth step, draw a line connecting end of shear stress lines like this. Now the final step of Mohr circle construction. Draw a circle assuming that the newly drawn line is diameter of a circle. So it will be like this. And this circle will be known as Mohr circle. A Mohr circle represents complete stress state of a two-dimensional object. Means on periphery of the circle you can locate shear stress and normal stress value of a two-dimensional object. So back to our basic problem. We want to find out shear stress and normal stress value at a given plane inside a body. And one thing to remember, angle in Mohr circle is always doubled compared to the actual case. If this is your actual case where you have to find stress values at angle theta, then in Mohr circle analysis the angle will be doubled. It will be 2 theta. And starting line of this angle should be the newly drawn diameter line. And you know, peripheral values of this circle will give normal stress and shear stress values. So at this given theta, this will be the peripheral value. So we can easily locate normal stress and shear stress like this. This is normal stress at this angle and this is shear stress at this angle. Now the information designers wanted maximum normal stress and maximum shear stress values. And you can easily note from this Mohr circle that normal stress is maximum at this point. So this will be a principal stress value and this plane will represent principal plane. It will be denoted like this. We are denoting it by sigma 1 and maximum principal stress is on this plane and about angle of the principal plane. If we take half of this angle, that will be the angle of principal plane in actual body. And you can also note that at this location normal stress is minimum. So this is again a principal plane, more precisely minimum principal plane. And one thing to note here is that angle between maximum principal plane and minimum principal plane is 180 degree in Mohr circle. So in actual case it will be 90 degree as shown in this figure. And if this system has to be in equilibrium, there should be equal and opposite stresses to balance this force. So the complete principal stress diagram will look like this, like a square, where these two stresses and these two stresses balance each other. And one interesting thing to note here, if we check shear stress values at principal plane, you can note shear stress values are zeros over there. Means on principal planes shear stress doesn't exist. Now designers' second requirement, maximum shear stress value. You can easily note that maximum shear stress occurs at this point and this will be maximum shear stress value. So it will be represented like this. Here it is. And value of this shear stress will be same as radius of the Mohr circle. And you can easily represent it like difference between sigma 1 minus sigma 2, that will be diameter of the circle, and by 2, so radius of the circle. This is all about two-dimensional analysis. So let's move to the 3D problem. Here it is. In 2D cases we are doing stress analysis on a square, but in 3D case instead of square it will be a cube. And these are stress values at the boundary of this object. And it has got 3 normal stress and 6 shear stress components. In 2D problem we have deduced a principal square inside the object, a square comprising of principal planes. Similarly here we can deduce a principal cube comprising of principal planes inside the object. It will look something like this. This is inside object, and in 3D case it has got 3 principal stresses, sigma 1, sigma 2 and sigma 3. And we usually denote maximum value of principal stress by sigma 1 and minimum by sigma 3. And shear stress values all over these principal planes will be 0. Now the big question, how to find out this sigma 1, sigma 2, sigma 3, the principal stresses for a 3D case? Well, there is no direct graphical method for this, unlike in 2D case. What you have to do, we have to rely on a analytical method that we will see in next section. In a 3D problem, if you want to find out normal stress values, you have to solve this cubic equation, which is in terms of sigma. You know, a cubic equation has got 3 solutions. Those solutions will be sigma 1, sigma 2 and sigma 3. And it has got 3 coefficients also, I1, I2 and I3. And values of these coefficients will be given like this. I1, I2, I3 in terms of stress boundary conditions. And I1, I2, I3 are called as stress invariants. The name invariance because independent of the coordinate system you choose, when you calculate value of I1, I2, I3, it will remain unchanged. That's why we call this as stress invariance. Now the second requirement of the designer, maximum shear stress value. And maximum value of shear stress for a 3D case can be deduced using a simple graphical method. Here what I have done, I have drawn 3 circles corresponding to 3 pairs of principal stresses. Means one circle between sigma 3 and sigma 2, another circle between sigma 2 and sigma 1, and a big circle between sigma 1 and sigma 3. And according to this diagram, maximum shear stress value will occur at this point. So I can easily see that value of that will be radius of this big circle, and that will be same as sigma 1 minus sigma 3 by 2. Hope from this tutorial you got a basic introduction to 3-dimensional stress analysis. Thank you for watching the video. Have a nice day.